wonderful topic, and I'll let you just take it away. So go ahead.
Thank you. Thanks, Shane, for the introduction. And I would like to thank you for the invitation. It's a great pleasure to talk about our research project on open source software innovation today. I would like to tell everyone that please feel free to ask questions anytime during the talk. I will also pause every now and then to facilitate engagement throughout. Before I start, I would like to acknowledge my co-authors. So this work is a collaboration between academic people and federal government organization. We work with colleagues from the National Center for Science and Engineering Statistics at NSF. And among the team members from our research division, I would like to highlight our brilliant postdocs, Brandon and Bywan, who did the medal work for this project and who have contributed to every aspect of the project that you will see today. So to start with, open source software is a computer software developed and licensed, but shared with a broader public that can change and distribute it for any purpose. So that's what we're going to be talking about today. The Open Source Initiative is an organization that reviews software licenses for compliance with this definition. And we're using this definition as our OSS definition in this project. This type of software is developed through the contributions of people from universities, government research institutions, businesses, nonprofits, as well as independent developers. Some examples could include Linux operating system, Apache server software, and Firefox web browser. While the extent and impact of OSS is currently unknown, recent estimates suggest that its magnitude is actually significant. For example, Apache, that is developed with federal and state funds, holds the largest market share of domains and active websites. Dr. Greenstein and Dr. Nagel have estimated that it would cost between $2 and $10 billion to replace these Apache servers with proprietary Microsoft software. And this work actually inspired the work that I'm going to be presenting here today. And Shane, if you would like to add something to that, please feel free to.
Thumbs up.
So our work is directly in alignment with current measures of intangibles, which is a huge topic in the national accounts. Intangible assets make a contribution to economic growth in an unknown quantity because they are not measured well currently. As I mentioned earlier, this project is a collaboration with researchers at the National Center for Science and Engineering Statistics. And CSCS provides statistics and data through surveys on R&D and innovation activity, and they also produce reports, including the science and engineering indicators. So one of their mission is to measure the research outputs of universities. As many of you may know, current measures used to capture research outputs are research papers, patents, and citations in universities, coming from universities. However, the development of OSS in these institutions is not captured by any current and comprehensive survey data. Despite its extensive use, reliable measures of the scope of OSS and the impact of OSS developed outside of the business sector are scarce. And this is what we're trying to address with our project. So we're aiming to measure better these knowledge assets with the data that we collect. So the good news is that many of the OSS projects are developed and maintained in open and free repositories. And the information embedded in these repos, including the code, the contributors, the development activity, actually provides a publicly available data source that we can not easily, in a challenging way, but that we can collect. By exploring these non-traditional, non-survey data sources, our goal is to improve indicators of research output and innovation activities in this project. So here are the questions that we want to answer. We want to find out how much OSS is out there, how much is created each year, who are the creators, which sectors they're coming from, and finally, the value of OSS as measured by its cost and impact. So these are the questions that we want to address in our project. So I would like to pause here to see if there are any questions so far.
Yeah.
And meanwhile, just to recap, what we're trying to do is that if you think of academia, research outputs are measured using citations, patents, and papers. However, there's a huge development of open source software by the researchers in these universities. And these outputs are not captured in any of these measures currently. So we're trying to understand how much that development is.
Yeah, question around how much is it created? Are you just going to focus on sort of counts, or are you going to be able to distinguish between counts and like measures of quality?
So currently we're focusing on the counts. That is even not measured currently outside the business sector. Within the business sector, there are some efforts from some of the federal government agencies to capture that information through surveys. However, as I said, outside the business sector, we don't even know how much is out there. We don't even know the count of these development activities. Any other questions? Okay. So first of all, let me define the scope for our project. Here, we treat as open source software any software project with an OSI approved license. I mentioned the open source initiative in a previous slide. Among the most common licenses are MIT, that was developed in this university, GPL, which is the general public license developed by the Free Software Foundation. Our goal is basically to develop an accurate method that is repeatable and scalable. Initially, we started with programming languages because we thought they would be a nice way to prototype what we want to do. It's not a really big world, so we can actually capture information about the packages that are developed for programming languages R and Python. And as you know, these are among the most widely used languages by data scientists and statisticians, so it makes a good story to focus on these packages. So what we asked was, can we take these two programming languages and estimate the cost of these packages? That was our prototype. That's what we started with. Then we wanted to scale it up to something more representative. We wanted to focus on all repositories developed and shared on GitHub, as it is by far the largest code hosting facility with over 31 million users and developers worldwide, as you can see in the chart as well. You can see the other source code hosting facilities, but GitHub is by far the largest one. So for both of these approaches, languages as well as the GitHub repos, we collect information from GitHub because it provides information on the development activities for these projects. So it includes development information, the lines of code that are added to each of these projects, the contributors, where they're from, and so on. So that creates a very rich data source that I mentioned before. So how did we first prototype? When we first started, we developed a data collection strategy for programming languages. First of all, of course, we start with our definition. Which packages are we gonna go after? Because that really defines our scope. As we said, we're focusing on OSI approved licenses and the projects that have these licenses. So we focused on these packages. We also focused on the packages that are production ready. That's what they are called in this space. They should be production ready and maintained because we did not want to include projects that are still in development or have stopped being developed before they were released. So we're really looking at the labels in these packages that says these are production ready and are maintained. We also wanted to capture packages that are used by a broad group of individuals. And that's the other reason we wanted to focus on these production ready and maintained packages. So what we did was we obtained a registry of these packages. So what is the list of all the packages that are written for R and for Python? So these exist in the package managers of these languages. So the package manager is a location that hosts, manages, and distributes OSS. So CRAN is you may have heard about it. CRAN, the Comprehensive R Archive Network, is the package manager for R, and PyPy, which is the Python package index, is the package manager for Python. So for R, we obtain, as you can see in the table, we obtain a registry of 13,000 packages to start with. And for Python, the list had 165,000 packages. So then, as I said, we focused on those that are production ready and that have a license approved by the organization, by OSI. So at the end, in this initial work, we obtained information about around 14,000 packages that we were able to use for analysis. And the reason we're, again, going to GitHub to find these packages is that GitHub is the place where we can collect information on development activity for these packages. So we can get to the commit information, which is the code edits for these packages, as well as we can obtain the license information and the contributors to these packages from GitHub. We have the full history of development. Any questions?
Yes. So GitHub only covers a small share of the packages, both in R and Python. Do you have a sense of which are the packages that get covered by GitHub? Presumably more recent, but maybe there's some other selection.
So actually, it may not be due to that it's recent, but people develop in different facilities that I tried to show. So there are other places where people develop, or some people just develop them in their machine, and they can actually post it on the CRAN. So you can develop your own machine. You don't need to be actually sharing it. If you don't want a Git version to it, if you do not need that, you can actually develop it and then apply to CRAN to publish your package, and they do all the checks, and then they allow you to publish it. So it's quite well regulated in the R space, actually. So they have these standards.
My question was more on the selection, because you are going to focus on packages that are developed through GitHub,
yes.
Right?
Yes.
So what packages are we missing? Are we missing certain types of econometric packages? Are we missing more machine learning packages? Are we missing more text analysis? Is there some selection into the packages that you're tracking that compared to the population of packages in R and Python?
That's a great question, but we have not really looked into that. Like, we have our set, and we also have the list of all the packages. We actually have the full set of packages that we were able to download from CRAN as a tarball, which we could use to get into. The problem is that you don't even, in many cases, you don't even know what those packages are for. That's why we're also developing some methods to categorize the packages. So you have the names of packages, you have some descriptions which you could use to extract the information about what the purpose of those packages are, but we don't even have that information currently. So it requires an additional work, but that's a great suggestion, which we should look into. Is there a reason for why some are published on GitHub versus not? Some are developed on GitHub, basically. Mm-hmm. Thank you. Yeah. Any other questions? Okay. So then, as I mentioned, once we figured out Python and R, we said, okay, this is feasible. Then we went out, presented out our work, and people started asking us, okay, so you have only 14,000 packages. What does it mean for the US? What does it mean for the world? So they kind of criticized our approach. So we did some thinking, and we decided, okay, why not go after all the GitHub repositories, since people seem to be using GitHub at a large scale. So that's what we wanted to do, to have something more representative. So that's how we wanted to scale this up. However, as you can imagine, it's quite a dramatic change to manage millions of projects, and the collection of this data is also very challenging. So I'm going to be talking about the data that we've collected, but I also want to stress the challenges that we had for the collection of and gathering of this data set. So first of all, there is a data set called GHTorrent project data that is publicly available that provides information about GitHub repositories and users. That was publicly available. So that's something we were able to use. However, that's not enough for our purposes. We actually need these repositories and we need the development activity. We need that information to be able to get to the value of these repositories. So only having the repo name is not going to be enough. Having said that, GHTorrent was useful because it has information about users, which helps us to categorize, to sectorize these projects to different places, countries, or different sectors of the economy. So, and GitHub, so to be able to collect the development information, GitHub provides an API that one could use, but it has its own limitations as well. So we, I mean the royal we, developed a package. He's here actually by our postdoc that I mentioned in the beginning, developed a package to scrape the most up-to-date information in a more efficient way than using only the API. So this is a developing code right now, and we're hoping to release that as well. So our data set provides the most up-to-date activity for each of these repos that we're considering. So having said that, eventually we obtained 7.75 million repos created between 2009 and 2019. And these are developed by 3.26 million distinct contributors around the world. So these are global values, right? So the bar plot on the left shows the exponential increase in the number of new repos created each year since GitHub started, which was in 2008, sorry. And we also wanted to look at the number of contributors per repo, because we are interested in the collaborations. What we observed was more than 76% of the repos had only one contributor, single contributors. And around 94% of all the repos that we consider, they have fewer than 5 contributors developing these projects.
So, Gizem, I mean, what I'm supposed to infer from that is that most of the projects with one contributor are probably dead, right? They're basically not going anywhere. They're not serving as coordinating large projects, but there are a small number of projects that are coordinating a large number of people. I mean, is that the right way to read that?
So, 76% of the, so you're asking the other way around, right? So, for people, how many repos they are in charge of? Is that the question?
Well, I'm trying to read, what am I supposed to understand from number of contributors per repository? I thought that in the examples where you've got a repository with large number of contributors, that's really a very active situation. Or am I missing?
Not necessarily. Not necessarily, right? So there are projects like 76% of them that have only one contributor, but these are for all the 10 years. So this is the cumulative data set. So I'm not giving you those numbers by year. So we can look at and see how it changes.
I see.
That's what you're asking, I think.
Yeah, okay. I guess it's possible for one contributor project to be still active.
Yeah. And yeah, we can look over the years how it works for larger teams versus smaller teams.
Okay.
Yeah, that's a good question. Okay, so as I said, our goal is to get to the value of these repos. So how are we going to do that? So what we did was, and this is where our collaboration with NCSCS and federal government is very helpful, we adopt a similar method used to measure non-market output in national accounts. So what they do is that they look at how much it would cost to create a package. So it's the resource cost that you focus on, because there are no market transactions for this. You don't have prices for these commodities, right? So that's what we're doing basically. So we're focusing on resource cost for their creation, similar to what they do in national accounts for non-market goods. So to do so, we adopt methods developed in software engineering for proprietary software. First of all, we quantify in our data lines of code added for each project. And this represents the size of the project. So here you're seeing the KOLC, that's the kilo lines of code that actually represents the size of the project. Kilo is 1,000. So 1,000 lines of code is what we use to get to the effort level. And as I said, this comes from the constructive COCOMO model that was developed in software engineering. So as you can see, there's a nonlinear function that maps the lines of code to effort in person. So the assumption basically is that, the effort increases as the project size is increasing. The rate of increase in the effort increases in the project size. So that's what it's about.
I have a question for you.
Sure.
Sorry, I'm just curious about code reuse. So if we're thinking about effort in terms of new code, or are we thinking, there's so much code reuse that happens in open source. So I'm just wondering how you're thinking about that.
So this is the development effort. So how much effort it takes for you to develop a code. And what they are doing is that they are using lines of code to get to that value. How much time it takes for you to produce a line of code, that's mapped to the effort in months, basically, person months.
Okay.
How many months of you would need to write a line of code? That's what this is trying to capture.
So do you capture, so what if, I write a line of code in one repository and then I just borrow that code and put it into another repository and reuse it? Like, how would you think, how do you, I guess, count that would be my question.
This is not captured here, and that's a great point. And we'll mention a bit about the reuse here. Reuse is a very nice measure for impact, right? It's like a citation.
Absolutely.
Yeah. And it's how these things actually diffuse, right, in the ecosystem. But here with this measure, we're basically just using at the development cost. We don't have any reuses. However, these estimates are done at the repo level. So looking at the details of the code, you can actually do more than that. Right now, every line of code is treated similarly, right? But you can actually you can also say each line of code could be different, right? Some are more complex, some are easier, some have different languages. So those could actually be taken into account by modifying the first line there. That's where you're actually using the complexity and the line of code to compare to the effort. And what you're saying is, again, the reuse, right? If you consider GitHub, you can fork, you can clone repositories, and you can use that information as a measure of reuse. And you can look at how much you add on top of what you've already taken from other repositories, which is what one could do, which is very, very interesting. But we haven't done that yet. Here, we're only looking at the lines of code added by people, but this is a great point. Any other questions? Maybe a good time.
Well, I'm curious because one of the characteristics of software development is that things get thrown away. So I have sort of the opposite question of to Becky's, rather than reuse. This is based only on what ends up being deposited. Is that correct? So it doesn't actually see the path towards that at all. And a lot of stuff gets thrown out on the way to getting to viable code.
So there's one thing, depreciation, that people use actually in the national accounts to get to it. But here we're only looking at the development. We're not looking at the repos that are, because we don't have the use information for
that. Yeah, because you don't have, yeah.
Right? We don't know who are the users. Currently, we're only looking at basically what would it take to create these packages. That's what we're doing.
Yeah.
But that's, yeah. And depreciation is something we're thinking about to get to the capital stock. of these OSs. And that's what we're doing right now. I'll mention that a bit as well.
So there's the other thing about this that's a little hard to get my head around, but I understand you have to do something. So don't get me wrong. It's not is there usually an organization around the development of software? Whereas this is a method that's going to treat it, it's as if it all comes from programmers who have no supervisors, but somehow just, develop it. It feels very, organization free, I guess is the.
And that's something we're trying to get to with the sectoral contribution. So we actually want to understand what is the contribution from the sector. So if you're actually writing the code for your organization, it's funded by federal government, let's say you're working on a project. So how can we find that information? How can we allocate them to the org? You could also be, as I said at the beginning, an independent developer just doing it for fun, right? You don't even need to be, you don't need to have affiliation. And that's what you're talking about. As I tried to mention in the beginning, so in the business sector, this is kind of taken into account. If you're developing a code for the company you're working for, your salary is taken into account, and that's kind of captured in the national accounts. But you're doing your research in the university and developing the code, but that's not captured anywhere, basically. And we want to understand what is the value of that investment.
Yeah, and just the last comment. So the other two concepts of value that I typically see, and I don't see how to do any of them here either, is value and replacement, right? So that if you wanted to do the equivalent and hire someone, that's not quite the same as what you've done here, which is fine. It's just a different notion of value. And then another notion of value is value in use. And again, there's no way to know that because you don't really have a market price and you don't have a quantity, right? So
exactly. So that's why we're using the approach of non-market goods. That's what they do in the national accounts. They look at the resource cost. Right. That's why we're focusing on it exactly for the same reason that you're talking about.
Yeah. Okay.
So then using the effort, we can get to the development time, how much it takes to develop using this the second equation there. And again, these are generic parameters, right? And we're taking them from COCOMO. There are different versions of COCOMO. We looked at the definitions of different software and found the one that applies to the open source software better. So that's the choice of our parameters. But again, as I said, you could actually play with these parameters based on the differences in your project. Given the information we can obtain about each project, we can adjust them. For example, we can look at the complexity, as I mentioned before. We can look at the language that are used. Some languages may take more time to write than others, right? So we can actually see on GitHub, based on the code, what language is being used for that code, right? And you can look at the team members, their experiences. So there are a lot of things one could do. This is currently the basic model that we're using. Okay? So once we have the development time, then we want to understand how much it costs then, right? So you have labor costs, and then you have non-wage costs. So we're again using methods developed in government aided, federal statistics to estimate these values. So we find the wages and we find the non-labor costs per month, and that allows us to get to the total resource cost for each project that we're considering in our data. I hope this was clear. Again, like we need to take something that people are doing, we need to adopt existing. If we also, in addition to this data collected, if we also, develop our own method, it will raise more questions than, we'll have less benefits than questions, I think. That's the strategy here. Okay, so what do we find? In our previous work, in our first work, right, with 14,000 R and Python packages, we obtained the total resource cost as $2.4 billion. And these were calculated in 2017 prices. Okay, so but what does it mean? So this is a simple initial estimation. So this means that if all of these packages have been created all in 1 year, how much you would need to create them. So that's what we're doing initially. So we're actually looking at the cumulative counts of these projects, their development, lines of code, and then estimating the value as if they are all produced in 1 year. And using the same approach for all the repos on GitHub that were developed for 10 years, if they were all developed in 2019, the resource cost would be $2.1 trillion. Those are the estimates that we get for the cumulative number. So you can see that it scales up by an order of magnitude for the GitHub repositories. And then, of course, since this doesn't make too much sense because we need to look at the depreciation over years and look at the deflators, what we do is that we take 1 year, let's see what happens when we look at it annually. And in just 1 year, the investment needed for the development of 2.6 million repos in 2019 amounts to $554 billion. So those are the values that we estimated with the data that we have. You have a comment, Shane? I see.
Yeah, I mean, the number is enormous, right? I mean, this is a stock.
Yes.
For a year, but it's really a sort of a flow as well. As a flow, it's just too big. Yeah.
And this is only the GitHub that's limited by the OSI approved licenses. So it's a lower bound, really.
So it's and I mean, if you put that up against, say, the value of the capital stock in software or the value of GDP in software, I think it's gonna, I don't remember those numbers off the top of my head, but I think you're in that neighborhood. You're like, so it just seems too big that proprietary software contribution to GDP would be of equal,
Yeah, so
it seems too much. I'm not sure why.
But that's good news because, like, when we, as I said, with our initial work, when we went out and presented, they said, okay, 2.4 billion. It's really not much. That's what they told us. So that's why we decided to scale it up.
Do scale. Yeah, no, I get it. Yeah. Frank and I encountered the same reaction, so I understand. But now you're in the other direction. Yeah.
Yeah. But we're using basically the lines of code, right? That, of course there are issues with that too, which I'm happy to mention during the Q&A. For example, anyway, let's mention that later, but I don't want to run out of time. So, but the last point here is that to fully understand the impact of OSS on economic growth, we have to look at it as part of an overall software capital stock, as I mentioned before. So to do that, now we're working on a new method that will take into account the depreciation and computer software deflators that will be adopted from the BEA. That's how we can actually talk about those 2.1 trillion is not the accurate number right now, but that's what we want to do to get to the overall estimate for the repositories. Okay. Any other questions about the method of the cost? Because everything will build on that estimation. Okay.
Oh, wait a minute. So what you just said was actually for the whole world, not just for US only. Yes,
this is global.
Yeah, so maybe the number isn't so crazy if it gets divided up a lot.
Yeah.
Okay. So,
and I'm going to come to, so our next step is exactly to understand the contribution of countries, contribution of the US, and how we can actually estimate that value, right? So yeah, as you said, what we've obtained is global numbers, right? And since repos can have developers from multiple countries, we need to find a way to estimate the contribution of each country, right? To do so, we're adopting methods from bibliometrics to estimate the contribution of each country. And I'm going to explain what that is. So that's called the fractional counting. So for example, when we consider published papers, and this is a method in bibliometrics, as I mentioned. So when we consider published papers with contributors from different countries, to measure research output of each institution, they use fractional counting. If there are two co-authors, let's say, affiliated with two different institutions, each country, each institution gets half of the credit. Okay, so you have co-authors and their contribution, the contribution will be allocated to all the countries that contribute to that paper. However, in most cases, as you know, in academic world, you do not really know how much each author contributes to the paper, right? You don't have that information. Sometimes people specify that in the papers. However, even then, it is very difficult to quantify the contribution of each author in the academic papers, right? So the richness of our OSS data is that we have information about each line of code added by each contributor. So you can actually map those contributions to their respective institutions and countries. So that's the richness of the data that we currently have. However, of course, there are challenges with assigning countries and sectors to the users, and that's what I'm going to be talking about. So what do? In order to map our developers to countries, we use the self-reported location information from the GHTorrent data that I mentioned in the beginning. Since these are self-reports, right? Because when you're creating a GitHub account, you need to fill out all the fields, and most of the people may not really care about those fields, right? So there's a lot of missing data. There's a lot of cleaning and standardization that we had to deal with, right? So you don't really care about how it's not a drop-down menu, but you actually have to enter this information on GitHub. And this is something that we had to deal with. Again, it's the royal way. This belongs to Brandon, who is also in the audience. I think that worked hard for weeks to be able to actually do all the regular expressions and working with the major cities, mapping them to countries, fixing all the spellings and whatnot. So that's how we were able to map almost 20% of the users in the data to countries. So we have a lot of missing information, of course, but still it's a really big number considering that the universe is really big, right? And this 20% corresponds to a third of the total activity that we were able to collect from GitHub, right? And the activity is the lines added. So we have all the lines of code added to GitHub, and we have the lines added by each of these authors. And then the ones that are not missing that we were able to classify as to countries makes up of 33% of all the activity. So it's not too bad. This is not bad. And so we see that in the bar chart, the majority of the contributions are from the US, and we talked about that a bit, it's really skewed towards US, like the data on GitHub, but this is what we observed, and it's followed by China and UK. So then we did the fractional counting that I mentioned. So each repo will have multiple countries, and what we do is that we allocate the cost for the repo to the countries based on the contribution, based on the fraction of their contribution. And that's how we get to the numbers, get to the cost estimates by country in our approach. Does that make sense? Any questions here?
Yeah, so two comments. So first of all, there's a sort of a tension here in that you're using US dollar, the way you did the estimate, right? You're using US wage dollars, but you're allocating it to Brazil, where the equivalent is going to be much lower.
Exactly. That's
and Russia and so on. So I'm not quite sure how to think about that, but that's a concern.
Yeah.
Yeah, and then, but it deflates things a little bit, one way or the other. I'm not quite sure how. And then the second thing, sort of, okay, so let's just take the US number on face value. you could benchmark, it seems to me, you could benchmark that number to see if it's in the range of plausible. So take the 195 billion, divide it by your wage rate, look at how many person hours that would imply, divide by 2,000 person hours per year, and then see how many people that would imply full-time employees, and then compare against, is it bigger than, is it, is it bigger than Microsoft, or is it, smaller than Google, or I don't know how to look at that number and benchmark it, but like benchmark it against a very, something like that would, but it seems like that's still relatively high. That still seems like a pretty large wage expense relative to a private firm. So.
Mm-hmm. Yeah, well, that's a great idea. So we'll definitely talk about benchmarking. What's the best way to do so? But those are the numbers we,
Hey, no, it is what it is. It's okay. Yeah. Don't get me wrong.
No, I'm not. I think this is, these are great points actually. Okay, so that's what we had for, and you're right when you're saying that these are all based on US dollars, US wages. All the calculation was done using BEA methods. That's for the US, but we need to think about ways to deflate those for other countries. Okay, so besides the countries, we are also interested in the sectors, right? Sectors of the economy, as I said. Again, this is global though, like we're not looking within the US, but currently that's how we started. Of course, these are steps that we're gonna be taking, but now again, we're thinking about the global data set, the data set that captures the global contribution. So here we're using the self-reported company field. So when you're on GitHub, again, you're entering your company, which is the organization that you can specify. You could make up things, but in many cases, people actually write their companies or institutions, as well as contributor emails are used here. So we actually look at the emails that people use for GitHub and use the domains, .edu, .gov, to be able to map them to these sectors. So these are the main things that we do. But there are, of course, additional other steps. There are many iterations, but this is our first cut at this. So what we find is that, most developers, we were able, based on our method, most developers were allocated to the business sector. So in the word cloud, we actually show the top 2,000 affiliations that we were able to identify in our data. So you can see that Microsoft is the highest, and that corresponds to 6,000 developers, and followed by Google and so on. So as I said, we have the missing data issue, and there's still some data that we still need to classify. We haven't done that. So there could be additional several thousands of users that may be business, but we haven't done that yet. As I said, this is an initial attempt, and we made some simplifications, shortcuts, but we still have some refinement to do here. So we're not very confident about all the sectors. But some sectors are better captured than others. So for example, academic sector is where we are pretty confident about what we got based on what people put in the company field and their emails, basically. So overall, using the same fractional counting method, we can estimate the development in the business sector as $128 billion. And in the academic sector, it's estimated as $46 billion. And you can see the rest, but these are the significant ones that we were able to obtain. Okay. As I said, we're more happy about what we have done, the certainty about the academic sector assignments. So I want to show a bit more about that and some of the challenges that we had to deal with here as well. So for this, we use GitHub users, self-reported affiliations, as I said, and emails. And again, it requires multiple steps, iterations to standardize these self-reported university names, right? Because one can fill out his university in many ways. So in the table, you can see some of the examples for UC San Diego that developers use as their affiliation in our data. So that's one of the challenges that we have. So you need to make sure that they are all referring to the same institution. And this requires some text mining and dealing with regular expressions, basically. And on the right, we're showing the top 20 universities by the number of developers on GitHub. You can see that UC Berkeley is on top with over 2,000 users, followed by MIT. And you can see Harvard there too. There's the number is like around 400 developers that filled out the affiliation field from Harvard. So this is where we encourage universities also to impose these roles for obvious reasons. So to better capture the university's contribution, if the developers actually have the practice of entering their university's affiliations, we would have a better time in identifying sectoral contributions, and universities could also get credits from that. Once we have the indicators in the longer run, that's if we think about it, if people actually start caring about OSS contributions in addition to papers and citations of universities, maybe that's one way people will have the incentive actually to tell their employees, tell their researchers to enter this information. So this is what we're pushing for. Any questions? I'd like to stop. Okay. And how much time do I have? Maybe.
You're doing okay. It's about 12:50. So
okay.
So,
Okay.
You know, 15, 20 minutes would be just great.
Okay, so here is the other side of the coin actually. So we looked at the value based on the resource cost, right? But having a high development cost for a project does not necessarily mean that the project is used a lot by others. And this comes back to the questions that were raised earlier. So what could be the measures that we can use to get to the impact of these packages? Because that also shows the value, right? That's the price that, you know, the willingness to pay on. We're not going there, but we want to find some metrics that can measure the impact of these packages. So when we think about the academic world, we think about citations, right? So why not citations here? So quantifying coding impact is an issue discussed in this ecosystem. People encourage citing packages that are used in their papers and whatnot. However, as you may know, it's currently not a common practice to cite the packages that you're using, although it should, but it's not. And moreover, when you want to cite a package, you don't even know how to cite it. So there are not established standards currently which people could use to cite packages. So citation is not a good measure for this purpose. First, we look at downloads as a measure of impact. And download information we don't have for GitHub repos, but we actually can obtain this for the packages for the programming languages that I mentioned in the beginning. So the table shows the top downloaded packages are packages that you can see. This was in 2018. Again, downloads as a measure has its own flaws. So you can download the same package in multiple machines, right? You could be downloading multiple times the same thing, the same person, or sometimes institutions can download a package. Many people can use that, right? So there are these problems with downloads. If you're trying to measure the number of people that are using packages, then downloads may also not be a good measure for that. But still, it's a proxy. So we still look at downloads for the packages. A second better measure that we think that we could use comes again from programming languages. So I don't know how familiar you are with the programming languages R and Python, but packages have dependencies. So when you're installing a package, it installs the packages that it needs to function as well. So this could be thought of as citations in the academic world, actually, because the packages are building on each other. They need each other. So in the second table, we're showing that, which are the packages that are reused a lot by other packages. So you can see that ggplot2, which is a very popular visualization package, has the highest reuse by other packages. The other thing to do, the fun thing to do, and given my background with networks, is that we can also generate networks using these dependency and reuse relationships. And we can study the structural features of these interactions using network analysis. So this allows us to identify influential packages. So if you just looked at the counts of reuses, ggplot obviously is the package that's most influential. But then there are other network metrics one could use to identify influential packages besides ggplot2. You can identify diffusion of innovation, right? Based on these dependencies, you can see from which direction is the innovation going to, from where it's going to, right? From which you have the information about institutions that are developing these packages. And you can actually see from where to where the diffusion is moving, right? So this is the snapshot of the network. Here again, nodes are packages. It's a directed network because it's a directed relationship. It's a reused relationship. So that's what we do. And another thing network analysis allows you to do is actually to look at communities. And this is something that was also asked before. So even if you don't know what these packages are used for in the data, you generate these communities looking at the interactions, dependency interactions, and these communities can tell you what they are used for. So different themes actually come up when you look at the communities of these packages as well. So that's another way how we can use network analysis in this work. Any question? Okay, so this is the final piece that I want to talk about. Given the richness of the data that we have collected, we can study other interesting activities in the OSS ecosystem, right? So NSF, for example, is very interested in international collaborations, the flows of science across and among international boundaries, and identifying specialization of countries. So we're also trying to understand international collaboration within the context of OSS. When we look at the academic papers, we've seen that international collaborations have increased, and government funding actually contributes to this increase, but it doesn't necessarily mean that there are more publications with international collaborations. However, they have shown that these papers have higher impact. So it's an important thing to have these collaborations. So we want to actually bring the same approach to open source software because we have the collaboration information. So we want to understand which are the countries that are more likely to contribute to OSS, which we already have started looking at, right? Which countries are more likely to collaborate across international boundaries? That's the second question we ask. What is the structure of this network? How does it change over time? Do we see it getting closer? Do we see countries getting closer or far apart, right? And which are the influential countries in this space? Which are the key players? This is something we can look at using the network approach that I mentioned before. So this is the same thing you have seen before. So we're working with the same data set. We have 700,000 contributors that we were able to map to countries in our data, and we have their development information that allows us to generate the networks of contributors, which I'm gonna mention. So we generate a contributor network where the nodes are developers, right? And edges correspond to the common repos that they have contributed to. So that's the network that we are talking about. So you actually have the collaboration. If you think about co-authorship network, this is very similar. Here, we're talking about repos, not papers. Then what we do is that we group the individuals from the same country and make that as a single node in our network. So then your nodes are actually countries in this network. That's the country to country network that we study after. Here, the nodes will be countries and the edges will be international collaborations between these countries. And we analyze these graphs using our iGraph package, gggraph package, and for visualization, we use Gephi. These are all open source tools, which we will make sure to cite when we publish this work as well. So here's what we see. So on the left, we're providing the descriptives of the network. So we have over 200 countries in our network, and we have 11,000 edges that you can see there. So in the table, you also see the density. So these are ties that are formed between countries over the potential ties that could have been formed. So what we're seeing is that 50% of the connections have actualized. So actually, it's a very dense network. So there are a lot of connections in this network. So there's high connectivity. Degree is, as I mentioned before, degree is the number of connections for each node. So the average here, you can see average degree centrality is 103, which means that each country is connected to 103 other countries on average. So again, this shows the high well-connectedness of this network. The second centrality measure we use for this purpose is the betweenness centrality. This is another centrality measure. It's not looking at the number of connections for countries, but it counts the number of paths that cross from a particular node to connect every other pair of nodes. So it's like bridges. So what is the capacity of a node to bridge separate countries? Okay, so you may not have a lot of degree, you may not have a lot of connection, but you could be in a crucial position such that if I remove you from the network, then the network becomes disconnected because you're actually connecting nodes that are in different places, disparate countries. So that's what we look at. So on the left, you see that countries are more or less similar in terms of degree centrality because there's high connections for every country. On the right, we look at betweenness centrality. And what we observe is that USA is the most central, influential country based on this measure. And these are the top 15 countries. We haven't shown the 200 countries, for illustration purposes, but this is what you can see here. And another thing we observe is that over time, actually, the top countries have higher betweenness centrality. So rich is getting richer. So it doesn't apply to the overall network, but the top countries are becoming more and more central, although the betweenness centrality for the overall network is staying constant. So that's somehow interesting to us.
Do you compare this network to either trade activity, like physical trade activity, or academic collaborations? I'd love to understand, whether we see more home bias, for example, less home bias in these types of collaborations, whether they're more diverse than what we see in the academic world or in trade data.
Yeah, so that would be a nice comparison. Of course, I don't have their structural features on top of my head, but one thing that I know is that, for example, as I said, these are very dense networks. There's high level of connection. So when we look at citation networks, for example, what we observe is that the density for those is 0.01. So it's really it's not as dense as these networks. So that's one thing we know. But it's very interesting to look at the other interactions between countries and to compare that to the OSS collaboration. And one thing to do definitely is the co-authorship, right? How does it work when they're actually writing papers? What kind of collaboration network, international collaboration network we would see if we consider papers rather than OSS? But this is something we want to do. So currently we're exploring our data, but these are really, really good questions to explore. Thank you, Natalia. Okay, so I think that's all I had. So we're showing that with our approach and the data set that we have generated, we can now measure an intangible that couldn't be measured before, that's not captured at this scale. We are creating a data set that is very rich. We're combining multiple data sources to generate this data set. And this This is a non-survey data source, which could actually complement and enhance indicators that are created for national accounts. So that's our main goal, right? So, and I talked about two important applications, the cost estimation first for the global development, and we try to allocate that contribution to different countries, to different sectors, and we're still making progress in that space. And the second thing is that we can use the contributor information and the collaboration information to look at these networks, try to understand how these groups, how these communities are formed, who are the key players in this space, and how does that diffusion take place, right? What are the flows of information? So these are the things that we can answer with this data set. And I also would like to, of course, invite you to think about what are some other things that we could do with this rich data. And the questions you have raised so far, I think they're all great suggestions, but we're happy to think about what other things we could do with this. And as I said, we're working on making this data set publicly available as well. So we want to actually give back to the open source community at some point. So with that, I can open to discussion and Q&A.
Well, I'll echo what Natalia just said. It seems like your last graph is most isomorphic to co-authorship networks. So one would be curious to know whether co-authorship networks look like this as well, or whether this is more collaborative or less collaborative. And I can actually think of two distinct co-authorship networks. One is the one you mentioned as a benchmark, which is academic papers, right, which would be very easy to do. It would just be laborious, but in the computer science community or engineering community, those are already available. So it's just tedious and laborious. But right, and then the second one, equally tedious and laborious, but also very feasible to do, is in patent networks. You know, among patenters, again, they have location like the US or the European patent data for all the inventors and all the collaborative networks.
Yeah.
Yeah.
And I will add one more actually that people have studied is the grant, you know, writing grants.
Oh, yes. Yes.
Another one people actually study. Yeah.
Yeah, I relative to patent networks, my guess is this is more collaborative. I don't know about co-authorship networks, but patent networks don't tend to be this dense. But I could be wrong.
We'll definitely look into that.
I mean, you know, the comparable part would maybe be the patent co-authorship networks among the parts of the patent data set that's affiliated with, say, electronics and computer science and software and so on. So try to get just the part of the patent literature that's most directly comparable, right? That would be the right benchmark, because who cares what happens in pharmaceuticals and mechanics, right? It's not really of comparable interest to this group anyway. I'm done. Yeah, that was it. Becky, you were going to say something, or?
Oh yeah, I one idea I'd love to know, like the last charts around reuse that you showed, and then looking at the collaborations. Are there collaborations that yield these really reused packages? So do certain kind of collaborations yield? And is it consistent with what, you know, there's so much work and innovation about which collaborations kind of yield the best kind of innovative outcomes? I wonder if we would see kind of a similar relationship here, or if we would see something different, and how kind of collaborations yield different types of value in terms of the reuse of different code packages.
Yeah, that's a great suggestion. So one thing that I didn't mention, but I cited those papers actually. For the same community, R and Python, we also look at the contributor network. So who are those that contribute to the same packages? And that's one way we actually, so if we overlap the two worlds, the two networks using some multiplex network. Then we can actually get to that. Which of these packages that are reused a lot have are also central in the contributor network, that have a high centrality because they contribute a lot. I think that would be a great thing to do. Thank you. Well, great suggestions here. This project will take another 10 years.
So here's a sort of a detail question. When you see so your allocation to countries is based on the sample of self-identified locations. So it's from either their email or from their affiliation, right? And so but then there's a huge fraction who don't reveal anything about their country, presumably because they either don't say something in their registration or they're using a Gmail account, which is then not indicative. Is that more or less the right way to think about what's happened here?
So for the, just with one correction, so for the country allocation, we use the location information. Here we haven't used the affiliation information, which is something we could do, but we don't see that the numbers will increase a lot. We're not going to, reduce the missing data, but we're using the affiliation and the emails for the other sectors.
Yeah. So did you check? I mean, don't get me wrong. It's not obvious to me there's an alternative available, but one would worry that it's representative of the type of, that it's a different way to say it. You could test directly whether the use of Gmail or the use of a specific country is orthogonal to the size of the projects, the type of the project, and other measurable features of projects. So that there's no correlation, so that you're not getting a selection bias of some sort.
Yeah.
Towards larger projects, or I don't know why you might, but you might worry a little bit that when the projects are company sponsored, like by IBM or Microsoft or somebody like that, it'll come with a company affiliation, and so you're getting a slight bias in affiliation with larger projects. I mean, that's the worry. I'm not so sure in practice that's really going to happen, because Gmail's everywhere, but nonetheless, we should
look at those correlations, and we haven't done that yet. So whether there's something, so whether a person not answering their email or information, what does it say about? So these are things we could actually study, right?
Yeah.
Different behaviors in this space as well. This is something we want to look at. The one thing that there's that trade-off that I see is people are creating open source software because it's flexible, right? You can make changes, you can share it. So people don't really want to be restricted with all these standards, practices that I was mentioning before. But on the other hand, it's good for them. So there should be some changes in the incentive scheme so that people are actually entering this information, right? So that people like us could use it, or their institutions could actually benefit from it. If they were being counted, as I mentioned before, then people will be more likely to enter the information. But it's something good to look at, that trade-off. Do you see different behaviors between people that do not provide information versus those that do, right? There could be, like, how do those teams look like? So these are all interesting questions.
Yeah, and then on your next slide, sort of a similar, the one with the universities, not this one, the next one with the specific universities. Yeah. But you have a value there, which you can use from the previous page, which you can assign to each university. At least on the US universities, you can compare that against the value of the NSF grants in the engineering and computer science community that go to those universities. I was under the impression MIT was the leader, not Berkeley, but who knows?
Yeah.
Yeah. And you could at least see, I would bet there's a positive correlation, if anything. But at least something like that.
No, I think that's also really good suggestion.
Because the NSF numbers are pretty available, right? Easily available.
Yeah.
So another question about contributors. Do you observe changes in affiliation for these contributors over time?
So there are, yes, and we actually, so we have also a category both for countries, I believe, and Brandon may chime in there, multiple categories. So if they change contribution, we can take the last, but I believe that we try to not make assumptions at this point. So we have categories where we say, okay, we still need to classify these are still missing, but we see some changes, but we haven't really looked at, we only focused on initially for a first cut, right? Let's consider those users that have one affiliation, one country, and then let's go with that. And then we want to improve later on. We didn't want to make some, but yeah, definitely that exists.
Yeah, that's great. That's great. I think it would be interesting to look at changes from, say, like a user or a contributor moving from an academic institution to a business setting and seeing if there are changes to the types of contributions they're making or which repositories they're making contributions to.
Yeah, that's also a great suggestion, making notes. Yeah. Thank you. That's a great suggestion. One of the things that we actually want to use to improve our sectoring is the Orcid database, that we can actually try to do a better job, and that can somehow capture the changes in affiliations of people. So that's on our list of things to do in the longer run, but that may get to what you're talking about, because then you can see the change of affiliation during the same time for the same user, if you can actually match it. So that's a separate project that we're thinking about.
Yeah, that's great.
Any other questions?
Wow. Okay. Well, that was awesome.
Thanks, Jim.
Gizem, that was just awesome. Very different. We've never had anyone do this before, so that was just moving in a new direction. It's it's awesome.
Yeah, it has its own challenges, but it's satisfying.
It's adventurous.
Yeah.
Yeah, lots and lots of. You're cutting a whole new path here. Yeah, Tommy's idea there, last suggestion was very good. There must be thousands of examples in here of affiliate or changes in affiliation, and so you would see behavior can correlate with that.
Yeah,
maybe hundreds, maybe not thousands, but it'd still be enough, you would think. It's a good idea. So, okay, so anyway, I guess we'll all thank you, and anybody wants to can hang out a little bit longer, but